In this video, we're going to be looking at some relationships that exist in an oscillating mass spring system. As a mass spring system oscillates in simple harmonic motion, the variables related to the mass are continually changing, but there are some facts that are helpful to know, like where do the maximum and minimum values for each of these variables occur? The displacement, the velocity, the acceleration, the force, the kinetic, and the potential energy. And we find that the maximum and minimum values occur at one of two locations, at equilibrium or at the end points x min and x max. Collectively, I call these maximum and minimum values spring facts. And you got to know your spring facts before we can move on. Hopefully after discussing them, you'll find that most are common sense. Let's start by looking at a mass on a spring that's oscillating horizontally. When a mass spring system is stretched and the mass is at position C, the displacement's at a maximum. And the displacement is positive because it's moved in the positive x direction. The restoring force is also at a maximum from F equals kx. And Hooke's law tells us that the restoring force is negative because it acts in the opposite direction as the displacement. And from F equals ma, if force is at a maximum, then the acceleration must also be at a maximum. And since the force was negative, the acceleration is also negative. When you're at an endpoint, the potential energy is always at a maximum because a stretched or compressed spring always wants to return to the equilibrium position. And if all of the energy is potential, it means that there's no energy left to be kinetic. So the kinetic energy is zero, and if I don't have any kinetic energy from 1/2 mv squared, it means that the velocity must be zero also. When the mass spring system bounces back and passes equilibrium, the displacement is now zero. And because I'm at equilibrium, the net force acting on the mass is zero, the acceleration is zero, and the potential energy is zero. All of that potential energy has now turned into kinetic energy, which is at a maximum. And when you have maximum kinetic energy from 1/2 mv squared, you also have maximum velocity. And as the mass continues from equilibrium to position A, another endpoint, you can see that we have the same max and min values as we did at position C, but this time the displacement is negative because it's moved in the negative x direction, which makes the restoring force and the acceleration both positive. The other thing I want to point out is the kinetic and potential energy, because their energy measures are always going to be positive values. We can also look at these same spring facts when we have a mass on the spring oscillating vertically. Looking at the vertical spring as a y-axis, the displacement is negative because I have pulled it in the negative direction. So if the displacement's negative, that means the force and the acceleration have to be positive. I have a stretched spring, which means I have maximum potential energy, so I have no kinetic energy and I have no velocity. And then when the mass spring system bounces back and passes equilibrium, temporarily the displacement is zero, the force is zero, the acceleration is zero, and the potential energy is zero. But all that potential energy has turned into kinetic energy, meaning that the mass is traveling fastest as it passes through this equilibrium position. And again, you can see that the spring facts at the endpoints are equal, with the exception of this time the displacement is positive because as I moved from B to A, I moved in the positive y direction, thereby making the force and acceleration both negative. The motion of a system in simple harmonic motion is sinusoidal. This means that a graph of its motion will look like a sine wave or a shifted sine wave, such as a cosine wave. This picture shows a mass spring system oscillating up and down vertically. Pretend that we taped a magic marker to the mass and that someone pulled a piece of paper to the left as it oscillated up and down. You can see the resulting sinusoidal graph. The x-axis shows time and the y-axis shows the displacement from equilibrium. We can also see from the graph that the system was initially compressed to set it into oscillation, and that the period capital T is the time for one complete oscillation. It can be a little confusing that the variable x is graphed on the y-axis of the resulting displacement graph. To sketch the corresponding motion graphs, just think through each position. For example, When the mass is compressed at position A, the displacement is positive, meaning the corresponding acceleration time graph must start at a negative point. And because position A is at an end point, we know that velocity must be 0. When the mass gets to position B, we know that displacement is 0, and acceleration is 0, and velocity is at a maximum. But how do we know if the velocity is at a positive maximum or a negative maximum? You can tell by looking at the slope of the position time graph. At point A, the slope is 0. And as the mass moves from point A to B, we can see that the slope is increasing. So we know that the slope is increasing, but in the negative x direction. That means that the velocity is negative. At position C, displacement is negative, acceleration is positive, and velocity is 0. When the system returns to equilibrium again, the displacement is 0, the acceleration is 0, and the velocity is again at a maximum. This time, however, the velocity is at a positive maximum because the slope of the position time graph shows that the system is speeding up in the positive x direction. Just thinking through these first few points should give you enough information to construct the corresponding graphs. You can always check your answers by knowing that the acceleration time graph is always 180 degrees opposite the position time graph, and the velocity time graph is always formed by shifting the position time graph pi over 2 radians to the left. Let's look at some vocab terms and related equations. The first term is amplitude. Amplitude is denoted as capital A and is the maximum displacement from equilibrium. So we can write x max as capital A if we want. A complete oscillation includes 4 amplitude measures, so we can count them 1, 2, 3, and 4. So amplitude is the maximum height above or below the x-axis. Next, let's look at 3 variables that are closely related. The first is period, and this is the same variable capital T that we learned about in circular motion. Period is the time for one complete something. So in this unit, it's the time for one complete oscillation, and period is measured in seconds. Next is frequency, F. Frequency is how many oscillations occur in 1 second. So period and frequency are reciprocals of one another. Period is how many seconds for one oscillation, and frequency is how many oscillations in 1 second. So the unit of frequency is 1 over seconds, or in honor of Heinrich Hertz, called a Hertz, which is abbreviated as Hz. And because they are reciprocals, the equation for period is 1 over f, and the equation for frequency is 1 over t. Angular frequency, omega, is similar to frequency. While frequency is how many oscillations occur in 1 second, angular frequency is how many oscillations in radians that occur in 1 second. So the units are radians per second, and since a radian is not a real unit, a radian per second is also equal to a hertz. And since one oscillation is equal to 2 pi radians, the equation for angular frequency is omega equals 2 pi f. The time it takes for a complete oscillation depends on both the mass and the spring constant of the spring. As an equation, we can write the period as t equals 2 pi square root of m over k, where m is the mass and k is the spring constant. We can also use this equation to derive another relationship related to angular frequency. Let's talk through it. So I'm going to start with this period equation, and I just took the square root of m over k and I broke it into 2 parts here, with a numerator and a denominator, and I wanted to make sure that the 2 pi visually was in the numerator, so I put it over 1. So I just rewrote this statement. We also know that period is equal to 1 over frequency, so I just made that replacement. And so now I'm going to solve for frequency. So frequency is the inverse of the period, so I can take this and I can multiply by the reciprocal, or I can take this equation here and solve for f by maybe cross multiplying. But either way, you're going to end up with this relationship here. So then I multiplied both sides of the equation by 2 pi. So I ended up with 2 pi f equals square root of k over square root of m. But we know what 2 pi f stands for. 2 2 pi f is angular frequency. So that means another way that we could calculate angular frequency is square root of k over m. That can be helpful because so far the only way we can get angular frequency is by knowing the frequency. But now we could get angular frequency by knowing the spring constant and the mass of the spring. So this is a helpful relationship. So I'm going to add it to our previous equation. It's also important to note that the time it takes to complete one oscillation does not depend on the amplitude of motion. So it doesn't matter if the mass oscillates up and down or back and forth a little bit or a lot, the period is the same. And even if a system loses energy over time, which is called damping and is shown as a decreasing amplitude, the period and frequency of oscillation remain the same. In a mass spring system, the period depends only on the mass and the spring constant of the spring. We can also write an equation that describes the location of the mass at any time during its oscillation. This equation is called the position function. The position function can be written in the form of x equals a sine of omega t or x equals a cosine of omega t. Let's look at each part of this function. X is the location of the mass on the y-axis. That means that what we're solving for is how far above the x-axis or how far below the x-axis is the mass at any given time. Capital A is going to stand for the amplitude of oscillation, and we're going to be replacing this variable with its appropriate value that we can normally read right off the graph. How do you know whether you should use the sine or cosine version of the position function? So that depends on where the mass is at the start of the story. If the mass is at equilibrium at the start of the story, then we're going to use the sine version. And if the mass is stretched or compressed, meaning that it's at an end point, we're going to be using the cosine version. Omega stands for angular frequency, and it's going to be equal to 2 pi f, and we will also be replacing this variable with its value as well. And then we still have t, which stands for time. In the position function, we are finding the sine or cosine of omega t, which is what makes it a function. So when you write the position function, we just keep the t. When we're ready to use the position function, we can then plug in any value for t to find the displacement of the mass at that given time. And one last thing, when you use the position function, your calculator must be in radians. This is because we are taking the sine or cosine of omega t, and omega is in radians.